You want further? Things are going okay, or it's very fast or slow? We are at the half. 3 days finished. 3 days more. Last day is for exam and evaluation.
Well, yesterday that was very complaint
You can go through the book and slides and some additional data.
Yeah. What's that? I don't know. He gave us the examples for the protein interaction or also gene expression. And I think this is better for us. But this is all of this from very computer and mathematical. Not
One point is that we need some interaction also. So at 12 there is tea break, 11:30 to 12. So that you can utilize, but no one is going and talking. Only one person is spending whole half an hour. So better you go and discuss your problems.
yeah, yesterday I suggested.
Similarly, today after lunch, from 2 to 3, he will be here. I will ask you to be here and we can sit informally. And if you have some your research related problems, like suppose you are working on some data, you want to model it, or you want to analyze it, at least you can discuss how to model it and how to analyze it. So try to explore your problems. If you have some research related issues, you can come and discuss. Is it okay or not? From 2 to 3. Then from 3 onwards, you can be outside to visit the campus, and then at home. So at least you can have a look on your problem that you are working, and then try to see what are the issues you are facing, and you can come and discuss. So this one thing I wanted to add, like there should be some more interactions. Similarly, if you want to go outside, those who have done PhD, they want to explore the possibility for postdoc, so they can talk at least. What are the ways to get postdoc? Similarly, those who want to go outside for PhD, so they can explore the possibilities. What could be the ways? What are the basic requirements? So this kind of questions you can frame in advance. And he will be here, one can ask, he can explain. Instead of one-to-one, better to, you can sit here, he will be here. You put your questions and he will answer. So one question could be useful for others also. Anything else you want?
So you written one exam after this whole session. What kind of exam it will be?
Actually, ministry wants, like for this course, for each course, there should be some credit. So generally 1 week course is for 1 credit and 2 week course is for 2 credit. So for giving credit like A grade or B grade or C grade, there is a scale also. So you need to give exam. So there will be comprehensive exam based on all the lectures. It will be 1 hour or 1.5 hours. Then you will check your copies. And accordingly you will get your percentage and grade also. Keep on revising what are the topics being covered. It's very important. On last day, there is 1 hour or 1.5 hour exam. Then there is break, and after that, the elective session. You will get your certificates. So you are going to get one certificate and 1 grade sheet. So grade sheet I will send you through courier or through speed post. But certificate you can get here itself. Because you need sign of Vice Chancellor also on the grade sheet. So we will evaluate, review grade, and then we will prepare your mark sheet, and that will be sent through courier. You are going to get some percentage also. How much percent you are going to get? And this will be the record of Jamia. This course was quoted during this period. This was the examination. This was the question paper. These are the answer sheets. And this grade you got. Anything else you want?
Excuse me, sir. The pattern will be MCQ. Paper
This is still you have to decide.
So what is
Some multiple choice questions. Maybe mixed.
we'll describe something. Let me think about it.
This is just like semester end exam. Not replace semester end. Be ready for that. And have you seen the book of Dr. Zaki? He has book also by Cambridge Press. Data mining. So these slides are the part of that book. These are based on those chapters. So you can try to get that book from online. It's freely available. On his website also, you can get the link. So from that book, you can go thoroughly through the chapters. Okay.
So, first I'm going to quickly sort of finish up this clustering thing that we did yesterday. So there's a few more things I just want to point out. And then once I finish that up, then we'll move on to the classification process. So last time we saw, two of these methods, right? So one was the spectral, so you try to model the graph, and then you try to do a k-way partitioning of the network. And for that we use these two objectives, the ratio cut and the normalized cut. And both of these were the minimization objectives. And then we looked at the Markov chain clustering, which used the transition matrix to walk through and to sort of dampen the walk as you basically as you go further and further, the less influences the cluster that you're trying to find. So let me just go back quickly to so today I want to describe a few other alternatives that you can use to cluster graphs. But one of the key things is, in terms of the objective for the spectral, for the partitioning approaches. So last time we had, these two, the two objectives, the ratio cut and the normalized cut. So this one, so this objective, right, this one is your ratio cut, the RC, and so sort of the intuition of what you want to do was that you wanted to minimize the edge cut, the weights, the weights on the edges from Ci to everyone else, to the complement. And then, so that was one objective. Then the other one was the normalized cut, where you do the same thing, but you do with respect to the volume of the cluster. So you want to maximize the volume. And so we just combine them into one objective. So minimize the cut, maximize the volume. And so I just want to have one objective, which is a minimization objective. So we put the volume in the denominator. So higher volume will result in lower values, and you have it. Okay, so this led to those matrices, naturally the Laplacian matrices, and you compute eigenvector eigenvalues. So obviously there are other ways of doing things. So I'm going to illustrate a few other, objectives just to sort of understand that.
Can I just ask a question?
Yeah.
From the k eigenvectors, how do you get the n by k matrix? You get the k eigenvectors.
Oh yeah. So that one is that once you get those eigenvectors, essentially what you're saying is that, so for every, so this one eigenvector is n by 1 vector, right? Okay, so I now have k of them, right? So what you're doing is you're just using the value, right? So each point is essentially the value for that particular entry, and you have k values, so you have k-dimensional points. Okay, so the question is that, we can think of many other objectives, so I want to mention one of them, which is the average cut. which is kind of like the reverse of what we did for the ratio cut and the normalized cut. So the average cut objective basically is it's sort of like the opposite way of thinking. Instead of minimizing things, we want to maximize things. And what we want to maximize is the internal weight. Right, so you might say that instead of saying that, minimize the edge cut from me to everyone else, maximize the internal weight. So that's what this basically said, that across the K clusters that we want to find, you basically take the internal weight. This is simply the weight of all the vertices, all the pairwise weights within the clusters. The weight from Ci to Ci itself. So in terms of our partitioning, we are basically saying that find me such clusters that have very high weights, internally. So this would be internal to C1. There should be very many connections, and it should be very dense. And so let's just focus on that. Let's not worry about the edges that cross over. Right. So for each of the clusters, just try to maximize the internal weight only. What would that do? So if you write it out in this format, and this also again the cluster size plays a role. You could have made that a volume also. It would have been a slightly different objective. So in one case you would get a. So in this case, if you actually sort of think about what this means, then you look at that cluster indicator vector, the Ci vector. So we can rewrite this in this manner. That actually this is what comes out of it. So the internal weight essentially can be written as in the adjacency matrix. So to think of it this way, that in the simplest case, if I can sort the matrix such that all the cluster 1 and so let's assume that I want to split this into two parts, and I can say all the cluster 1 entries should be here. Okay, all the cluster 2, just we can just commute the nodes of the matrix without changing anything as such. If I were to do that, it's basically like saying that I just want to look at this part, and I want to just look at this part. Like how many weights are internal, right? So actually that is pretty much, you're saying multiply by the cluster indicator vector on the left and on the right. So things that are 0 will drop out. Only both sides have to be 1. The rows and the columns, they belong to cluster 1. All those weights will be added up. So that will be exactly, so this part here would be C1 transpose A C1. This combined weight will be actually that term. So to see that, you can actually expand it out and write it out and see what that means, but that's what it is. So you're basically trying to maximize that. So this objective then just becomes a maximization objective. And it turns out that naturally now this is essentially like getting the eigenvalues on the adjacency matrix. So one can do this. But the problem with this approach is that the adjacency matrix doesn't have the nice properties of the Laplacian. Like we saw last time, when we looked at the eigenvalues, you can have negative eigenvalues. And so the question is, what does that mean, right? So a negative eigenvalue is not very useful, because normally we use the value as a sort of the notion of goodness of the objective function. So in that case it was minimization, so we were looking at small values. Here we want to maximize. And so if you want to maximize and the value is negative, it's like there's a contradiction here, right? So typically what you have to do in this case is you have to ignore all the negative values. You only look at the positive eigenvalues and the eigenvectors, corresponding eigenvectors. So that's one objective. But actually here's the more interesting one. This is a very important objective, and I'm writing it out as an objective, but actually I don't think I have slides, but it's in the so let me actually explain what this is, because modularity. So there was a question that someone asked me yesterday, that how do you evaluate the clusters? Okay, so you run all these methods, you find different clusters, right? So I can use ratio cut, normalized cut, and some of the other methods I'm going to talk about today. So you can run all these methods, but there should be some sort of scoring metric, right? How do we judge how good your clustering is? And so modularity is actually used in that context. Here I'm using it as an objective, but actually modularity was used to evaluate a cluster. So given a graph, you partition it into k parts, and now you want to check how good your cluster is. So let me talk about it in that context. Then I'll come and refer back to here that we can actually directly try to maximize that objective if you want to. But let's say how to evaluate a cluster, like a graph cluster. So this is basically using modularity as a way to evaluate. Okay, so the idea is that, you have a graph, you partition it into 3 parts. Here's cluster 1, here's cluster 2, here's cluster 3. Okay, so different methods give you different clusterings. So we want to sort of judge how good the clusters are. So modularity conceptually is a very simple, or rather, what it tries to do is the following thing. It says, I'm going to see how many edges are there in the cluster. Okay? So this would be the observed number of edges within the cluster. And then I'm going to contrast this with what I would expect under random chance. So just by random chance, how many edges would we have expected? So it's kind of like a chi-squared measure in that sense. In chi-squared statistics, you do the same thing. You say, how many times do I observe certain things happening? And then how many times would I have expected them to happen under independence? And you compare those two. So modularity is pretty much something like that. So let me, actually, since I don't have the slides, I'm going to use the book to try to explain this. So let me bring it up. Okay, so the actual formula is as follows, and then we'll see what that means. Okay, so the modularity is defined as follows. So this is, like I said, it's an evaluation metric, and then later on we'll use it as an objective. So, so this is the Q. So they use the Q score for it. So the idea that you have these clusters, you have these K clusters, K clusters or partitions. Okay, so we define the modularity as follows. It's basically the observed number of internal edges, okay? Or observed fraction of internal edges. So this would be the sum over, I goes from 1 through k, and this is W, Ci, Ci. So this is the total internal weights, right? So for cluster I, all the edges, so remember WCI, Ci means one point in Ci, the other point also in Ci. So it's all internal edges and the weights on those. So that's the sum total of all the weights. And we look at the fraction. So the fraction is basically over the entire graph. So what fraction? Okay, so VV means any vertex, any other vertex. It's the sum total of the entire matrix. All the weights, if you simply add them up, that will be WV, comma V. And this is the internal weight. Okay, so this part is what you observe. So this is the observed part. But after the clustering, this is what you observe. Okay, but now we have to come up with the expected number. So I want to know how much would you have expected just by random chance. Right? Each edge can happen if you make the assumption, right, that my graph was random. So in a way, they wanted to contrast this. So this is what I was referring to maybe 2 lectures back. That for many of these graph analysis types of questions, if you want to sort of evaluate how good you are, you have to compare with a random, scenario. You say, this is what I observed in the real world. Here's what I would have expected to see by random chance. And then we contrast those two. And the further you deviate, the more statistically significant you are. So in a way, that's pretty much the same idea here. That we see what we observe, and then we basically take out what we expect by random chance. So what do you expect by random chance? So let's see. You have a cluster, right? And you can look at the fraction of the volume within the cluster. So I need to compute something for expected. Expected fraction of weight. And this is the observed fraction of weight. Okay, so what is this? What is the? How can I compute the expected fraction? I guess. So let's look at that, and then I'll plug it in here. So what we want to do is the following. So for the expected fraction, you have to say, okay, I have this cluster C1, and I'm going to basically see how much of the weight is internal, how much of the weight is captured in general by C1, okay, across the whole thing. So let me first look at this ratio. WCI comma V over W V comma V. What is this fraction telling me? This is telling me, if you start at cluster 1, right, so from cluster 1, and look at the rest of the clusters, maybe it's, like there are 2 clusters, so this tells me the total weight from C1, so how much of the, essentially this is the volume of Ci, right? That is internal or external. And so we can use this as the probability kind of like of an edge, so to speak. Okay? So you can just use this fraction as, if you were to pick an endpoint from Ci or from C1, this is the proportion in which you would pick it, right? So it's across, because we are dividing by the total weight, right? And this is the weight of that cluster totally. So you can think that what is the likelihood of picking a node from this cluster? It's kind of like proportional to this, So that's pretty much the intuition, that this is kind of like the probability of picking one endpoint from Ci. And so now you can do the same thing. What is the probability of picking an endpoint from something else? And you just multiply them, that will give you the expected fraction of weight that you would have. If randomly you were to add edges, you would pick one node from this cluster, one node from another cluster, and you take the product, that would be the expected probability. So the expected probability of internal edges is simply, so just think of this as, Pi, is simply Pi times Pi. This, I want to know internal probability. This is simply the expected fraction of weight, okay, that I would have expected to see by random chance. So you observe something, this is what you expect. And this is exactly, Pi squared is the value that we put in here. So it's simply this ratio times, squared. So it's W Ci comma V over W V V, and the whole thing squared. So that's the expected fraction, or expected, if you want to think in terms of just binary, this is like the observed number of internal edges. If all the weights were 1, right? So that's probably easier to think about. If all the weights are 1, this is simply how many internal, what is the fraction of internal, like how many internal edges you have versus how many internal edges do you expect. Okay, so it's just, it becomes a number if everything is a 0, 1. Otherwise it becomes the fraction of the weight. Or the square, because you want to pick the 2 endpoints. It's like, if this is pretty much the chance of picking one vertex. So, for any edge you need the 2 endpoints, right? So we're saying that I'm just going to see what is the probability of picking a vertex. So this ratio, if everything is binary, it would be what is the likelihood of picking one endpoint from this vertex, and the likelihood of picking another endpoint from the same vertex or from something else. But it will be proportional to the total degree. So this will actually become the sum of the degrees. Once if everything is just 0, 1, it will be how many edges there are from this cluster to anyone else. And so we use that as the probability of picking a vertex from that from that cluster. So actually you can work it out a little bit more in detail, and then it becomes a little bit more clear, because I'm sort of working backwards from the formula. If you go forward, it's actually much clearer, but it will take a few more steps to get there. Maybe I can look at that. So that might help clarify some of these things. So anyway, so I think I'll come back to that.
So this is the probability of filling an edge. What is it?
This is the probability of
Within cluster edge.
actually you should think of this as the probability of picking an endpoint from that vertex. So it's like a probability of picking a vertex from that cluster. And so probability of picking another vertex would be the same, and then you multiply them to get the edge between them. So I think at this point probably needs a little bit more clarification. So I'll work out the steps in a minute. But this is the formula for modularity. So this is a very famous sort of evaluation metric. So for graphs, oftentimes when you have a clustering, they will look at what is the modularity score. And so the higher the modularity score, because you want this deviation to be large. So what you observe, the internal fraction should be much more than what you expect by random chance. So the higher the modularity, the better the clustering. And so that way you can rank, which method is doing better, which is doing worse. And before I actually derive this thing completely, this metric itself, it turns out you can actually use this metric itself as a in the spectral method. So you can say, instead of using it for evaluation, I'm going to use this objective. So just call this the modularity objective, because it has all those same things as before, right? The weight, and so you can actually rewrite this, and it turns out that this can be expressed as a maximization problem, because you want to maximize the modularity. And so this is what I have here, is that there is just after you do all the manipulation, you plug all the, so this is pretty much the same thing, this is the Q, the modularity evaluation score here, but I'm using now the, a new matrix to represent that. So it turns out that after all the manipulation, it turns out to be another matrix. Okay, it's called the modularity matrix, and you can compute the eigenvectors of that. But unfortunately, this modularity matrix also doesn't have the nice properties of the Laplacian. So it can have negative eigenvalues. So again, you have to do the same thing like we did for the adjacency. So this is just to show that there are more than one way of defining an objective. Certain objectives are much easier. They're more sort of mathematically nicer. Some of them are not that nice, but we can still do things with it.
Sir,
Yeah.
sir, is it analogous to verifying if a particular node is in a particular cluster? The verification.
The verification. Okay, so one thing to keep in mind is that this evaluation is purely sort of unsupervised. Right? You do not know anything about the ground truth. If you knew what the ground truth was, then you can use that information. This is just from a structural point of view, right? We're just saying that a clustering, that basically has more observed internal edges than what you would have expected is a good cluster. And the higher this is true, the better off the clustering is. So it's a purely internal measure. There is no external information. Okay, so let's actually derive this. So because this part is it's actually a good sort of exercise. So let me start with a simple. Let me start with a binary example first. That is, you just have an adjacency matrix that is 0, 1, because it's easier to see in that context. Then we can add the weights. So you start with the adjacency matrix. So A is the adjacency matrix. Okay, and then you have a clustering, right? So you're given A and you're given the clustering, C1, C2, Ck. So these two are basically given. Okay, so first I need to know what is the observed information. Well, the observed part is easy. The observed is simply across all the clusters. You can see how many edges are there within a given cluster Ci. So pick Ci. I want to know the number of edges within the cluster. So the number of edges within the cluster, and now I want to know the exact number of edges, right? So this is actually if you, so if I use my cut information, this would be CI, but you have to divide by half. Because the point is, right, when I pick an edge, I mean the two endpoints, the same edge will be counted both ways. So you have to divide by half if you want to know the number of edges within the cluster. Okay, and also I'm going to use so this you can actually expand out. You can say that actually half of, of course, x belongs to Ci, y belongs to Ci, is the adjacency matrix, entry AXY. Right? So just sum of all the internal, actually, yes. So this would be 1 or 0, and that will give me the number of internal edges. Okay, so anyway, this is the easy part. Now we need to get something for the external, right? Now for the expected, like what is the probability? So let's derive that part because that's the more interesting one. So okay. So you have, I want to pick an edge, right? An edge has two endpoints, so I have to pick one endpoint and the other endpoint. So first of all, the probability. So if you have a node here, the probability that this node will be chosen is going to be proportional to the degree of that node, right? So if you're picking at random, right? So remember, I have to pick at random. So obviously, a node that has a higher degree has a more chance of getting picked because I'm going to pick an edge, and this is going to be the endpoint with more likelihood. So what is the probability of picking, let's say, vertex x as one of the endpoints? So the probability of picking x as an endpoint is actually simply p of x equal to the degree of x divided by the sum of all the degrees in my graph. So this is across the whole network, right? This makes sense, right? So if I look at the sum of all the degrees, this will tell me the proportional. This is the probability that this edge, this vertex will be picked up. So this is the probability of picking that. And now if you expand this, it's simply the degree of x divided by the sum of all the degrees is actually 2 times the number of vertices because every edge contributes to a count of 2. So this is actually 2 over m. So this is the sum of the degrees is basically 2m. So this is our probability of taking x as an endpoint. Oh, so remember the graph is fixed, right? So I cannot change the graph. So it's like saying that in the graph, right? Imagine those edges are there, but I have to now pick one edge, right? So what you're asking the question is that if you pick an edge at random from the graph, what is the likelihood that you'll pick x? Right? So if a vertex has high degree, it will have many edges. That means the chance of picking those edges will be higher, and so the chance of picking that vertex is going to be higher. So essentially, it's proportional in that sense. So it's actually a very good question because that's part of the sort of the analysis is that when you do, so this is given a fixed graph, you will pick that vertex in that with that probability as one of the attributes. Okay, so once we have that, then of course we can say what about x, y, right? So what is the probability that once you pick, one endpoint is x, the other endpoint is y. So I want to know what is the likelihood of that. So that will create the edge between them. So the probability of picking the x, y, is simply this times, the degree of y. So we can say probability of x, y. So I'm just going to call that the probability of x, y edge. Okay, so let's just write it as x, y. This is the edge between x and y. Okay, is going to be simply p of x times p of y. Right? Because things are happening independently. So I'm assuming it's completely independent. The two endpoints are chosen independently. And so this will simply be d of x times d of y times 4m squared. Okay, but now I want an expected value. So you can think of it this way. You can think of it this way. You're going to do m trials. Okay, you're going to do m. You're going to pick m edges, and for those m edges, there are 2 endpoints. Okay, so there are actually 2 m things you have to select, and this is the probability of success. Okay, so think of this as the probability that that edge is going to be chosen. So it's basically saying that you're going to do 2 m trials with this as the probability of success. So this is actually a binomial distribution with this probability as the probability of a success. So you can then do the expected, so you can say what is the expected number of, what is the expected number of edges in my, expected number of edges between VR and VS. So this would be, so you say that there are 2 m choices, and this pxy is the probability of success. So remember, we are assuming that the same edge can be chosen multiple times. Okay, so there's no assumption saying that once you've chosen it, you cannot choose it again. We're just saying blindly pick 2 endpoints. Okay, and I mean basically, so we want to know how often x and y will get chosen in this process, completely at random. So that would be the probability. So the expected number of times that you choose x and y, so this is the probability of success. So this would be the expected number of edges between x and y is simply 2 times 2m times this probability of success xy. This comes from the binomial distribution. Right, so the number of trials times the probability of success is your expected number. And so if you plug this in, this basically boils down to dx into dy over 2m, right? The 2m here and the 4m squared, 1m and the 2 cancel out. So now I have basically, the key idea is basically here, that I want to know how many edges can there be completely at random between 2 vertices x and y, and that's the number of edges between those 2. So now I just have to sum them up over the whole cluster. So once you do that, you basically say, okay, so the expected number of edges in cluster I is what? So the expected number of edges in any given cluster is then going to be sum over all vertices x, sum of all vertices y. It's going to be this thing, dx times dy over 2m, and then you have to take half because x and y are interchangeable. Sometimes the role of x and y is so either way you can choose it in both ways. So you just do it by half. Because this sum and this x and y, one time the y can also be the same vertex, x can be the same vertex. So you've actually counted everything 2 times. So this is the expected number of edges. And so now you have basically the formula, right? So we have a formula for the previous one, which was the observed number. The observed was right here. And so now you just subtract and you're done. So the Q is basically sum over all the clusters, not just not just one cluster. And then you just plug in what do I know about the observed number within cluster is this one. Okay, so AXY, so half of sum AXY, x belongs to CI, y belongs to CI, minus what we just did from the top, which is this one, half x, y, and dx, dy over 2m, and this is all within CI. And so this is the observed minus the expectation, and then now we just take the fraction. Okay, what is this? So the modularity is actually this difference divided by the total number of edges. I'm sorry, the total number of, the total degree. So this is just to make everything into a fraction. So what fraction is internal? So this was the number, right? So I'm just saying what fraction of that is internal under observed condition, under expected conditions. And so this is the formula for modularity. And now if you actually plug in what we know about the degree, okay, this will turn out to be exactly that formula that we had before. So once you plug in, once you sort of rearrange the terms, this can be written as, so this is just pretty much manipulation of this formula. So this formula is going to help us. So Q ultimately becomes the sum I goes from 1 through n. The observed part is simply WCIV over, CICI over WVV minus, and then this one will just become a square, right? The 2 degrees, right? That's where the square comes from, essentially. And so, this m, so there is a 2m here, there is a 2m here, right? So you see the dx by 2m, dy by 2m. So if I move it inside, and if I take this 1 over 2m and move inside, this will become half sum dx over 2m times dy over 2m, right? And that will give me this this expression here, W CIV WVV squared. So that's the WVV part, okay? And the degree, if I sum up all the degrees internal to the cluster, it will be WCIV. Question?
What is K?
K is the sorry, not n. Yes, it should be the number of clusters. Yes. So you're doing the sum over all the clusters, right? So let me quickly backtrack and just recap. So then we'll So what we did is essentially we said your graph is fixed, your clusters are fixed because you already discovered them. And so now you just want to know how many, what fraction of edges are internal, what fraction are external. I'm sorry, what fraction would I have expected by random chance. So then we basically model this as a binomial process. Basically say, pick any vertex at random, and the probability of choosing that is proportional to the degree. This is always true in any random. So this also happens in a random walk, by the way. If I give you a graph, and you do a completely blind walk in this graph, the chance of visiting a vertex is, you can prove that it's proportional to the degree of that vertex. Okay, so it's pretty much the same idea here, that if you pick things at random, then the chance of picking that vertex is simply the degree divided by the total degree, and the total degree is simply 2 times the number of edges. So we have that formula for the probability. And so now the probability that x is chosen and y is chosen independently of each other, right? There's no influence. You can't say I'll choose x first and then y later. It's just like 2 of them are chosen. So what is the likelihood that there's an edge between them? So once you choose them, that's basically the kind of like the probability of having an edge at random. So now you're asking at random what would have happened. So you just multiply them out. And you use this as a success probability. You say, okay, now this is the probability that x and y, that there might be an edge between x and y. Okay, if I pick things completely at random. Okay, so that, then you use this probability as a success probability, and there are 2m choices that you have to make, and so this becomes a binomial distribution, and so this is the formula for the binomial distribution. The number of choices times the probability of success is the expected number of times that will happen. And so that's our formula here. Alright, and then you simply, so now that I know it's x and y, you do it for the whole cluster. Across all x and y, how many edges do I expect to see? X and y are internal to this cluster. And then because x and y can both be one or the other, so we counted things twice, so we divide the half. And then you just plug it in, you do some manipulation, and the formula basically comes out. Okay, so any questions on this part? Alright, so anyway, like I said, the modularity is a very interesting sort of a measure because it gives you this sort of a significance. So you might sort of think of this in terms of sort of a proxy for statistical significance of the clustering. Alright, so that is what I wanted to say on this side. Now, a few more algorithms and then I will stop. So one other, so far we have sort of looked at purely spectral and sort of Markov-based approaches. You might say, why can't I use just sort of the graph information directly? That is, let's not worry about matrices. Let's just use the graph itself to come up with something. So one of the early approaches, this came from the physics community, was this Gerber-Newman algorithm. It's actually very simple, but I'm just going to sort of just mention it sort of for historical purposes. Because it's not a very efficient algorithm, and I'm not, it's sort of, but the sort of the main contribution of this, approach was really the modularity. So Gerber and Newman are the guys who proposed the modularity score, and since they did it, they were the early ones to do it. It was sort of used subsequently in many works. So the algorithm itself, like I said, it's not that useful in today's day and age, but the modularity score, that is the main contribution if you look at the sort of the fundamental, sort of the lasting contribution of this work. So the algorithm itself is like this. So you want to, they're going to eventually evaluate the modularity, but this uses the notion of betweenness. So this is sort of also a good tie-up with something we did from the first part of the first lecture. So they use the betweenness score of an edge. Okay, so you compute edge betweenness, and you basically use that information to create clusters. Okay, so the idea is to use, so given a graph G, so you're given a big graph G, you're going to first compute edge betweenness. For all edges. Okay, so now how do you compute edge betweenness? It's pretty much the same thing, except for the vertex, right? For the vertex betweenness, it was how many shortest paths go through that vertex. In this case, it would be how many shortest paths go through that edge. So you look at all pairwise, so here's an edge, let's say I and j, and you look at every other vertex, in the graph, and you say how many shortest paths go through this one, So that would be an indication of the importance of that link. So their idea was, what we'll do is, we'll selectively remove edges from the graph, okay, one by one. And it's actually as simple as saying that compute the betweenness value for every edge and remove the most between edge. Right? So this has more chance of disconnecting the network. So basically, compute all the betweenness. So that's step number one. So actually, let us say, step number one is compute edge betweenness. Second step is sort in decreasing order. And third is, actually you don't need to sort, I guess you just need to know the max. Okay, I'll just say remove the max, remove the edge with maximum score. And then third step is repeat 1 and 2. So, you keep on removing edges. This is actually, in that sense, a very simple algorithm, right? You just keep on removing an edge. You remove another edge. You remove another edge. If you want two clusters, the first time the graph basically splits into two components, that's your answer. Right? So keep on removing till you get k clusters. So I would say repeat 1 and 2 until have greater than or equal to k clusters. Because sometimes you cannot control. Sometimes when you remove the edge, maybe you get many components, and whatever you get is what you get. So now the problem with this approach is this: that you have to repeatedly, right, every time, the problem is every time you remove an edge, you actually have to compute the betweenness for the entire graph, because you don't know exactly how this guy influenced everyone else. So this is where the real complexity of the method comes, that betweenness is anyway like an n cube kind of a computation, or n squared kind of a computation. And you're doing this repeatedly, so this becomes the O n cube algorithm. Okay, so the complexity of this algorithm is O of n cube, which is, I mean, you can forget about doing this in a large network basically. So there are two ways of improving this. If you say, I want to do this idea, well, number one would be, do not compute the exact betweenness value. Compute some proxy for that, right? So can you approximate? So the idea there would be that you do sampling. So pick any two vertices at random and see does it go through this one. Pick some other vertices at random, see does it go through this one. So this way we can actually, you have to be a little bit more principled about it, but this way we can actually estimate scores. So you have to do not exact edge betweenness, you have to do sort of a proxy for that, like an estimate for that. And if you can do the fast estimation, then this can be kind of made somewhat practical to do. Okay, still going to be n squared type of a method, but n cubed is definitely not feasible for very large graphs. Okay, so like I said, that's why this method is there. I mean, it's a famous algorithm, but I think it's famous mainly for the modularity score, because they then, they show that this actually gives you clusters with relatively good modularity and so on and so forth. So it's a very expensive method. Now I'm going to describe one other algorithm. This is from the Baravasi group, or actually one of Baravasi's students. This is called the click percolation. Now the click percolation is, as the name implies, it's sort of combining two concepts, right? Percolation is a sort of a physical concept that, how things sort of diffuse, okay, how they percolate. So there's a whole theory behind, percolation per se. But this is sort of percolation applied to graphs. And it's applied to graph in the sense of, first finding these. So this is more, I would say this is kind of like identifying, more like a community identification method, as opposed to purely a partitioning method. So far, all the methods we've seen, they're actually partitioning, right? So they're actually getting you these clusters. The click percolation is sort of more like, I'm going to focus on the dense region of the network. So identify the dense parts. So this is just a little bit of a hint at, some of the methods for community discovery. So this is not really a partitioning method. It's an example of community discovery. So this is, I'm not going to give you too many methods in this sphere, because there are a lot of other approaches also. But this gives you at least a flavor of the types of things we can do. Now, community discovery, it's very close to finding clusters, but except that in this case we want clusters to be dense. Okay, so community essentially you can think of it as, in partitioning you pretty much partition the entire graph, and you call that a cluster. But a community is a highly densely connected, maybe highly weighted group. And the goal is not really to partition the entire network, but the goal is to find these dense structures. So it's very close, but not exactly the same problem. So here the idea is that they said, okay, let's start with these cliques. And clique is the most dense structure you can find, right? It's at density 1. So, you have a clique of size 3, a clique of size 4, and so on and so forth. So obviously, it's a complete subgraph. So what they say is, okay, what we're going to do is, we are going to first discover all the cliques in the network up to a certain size. Okay, so let's say you fix the size, and you say the size, so I'm going to use a different, so I'm going to use the size, but that's okay. Normally here the K is actually used for the click size. So you give me the threshold, you say find up to 5, okay? So I'm going to enumerate all possible clicks up to 5. Now once you have that, then you start forming these, you start forming basically, so that's the first part of the algorithm, that find the clicks. The next thing is the percolation idea. The percolation idea is that if you find two cliques that share a large fraction of the vertices, then you basically merge them into one cluster. Okay, so it's like saying that, supposing you start with, and what is the condition? The condition is that you must share k minus 1 vertices. Okay, so only one vertex is allowed to be different, for example. So if you find another, so let me do it here. So supposing you find another vertex. Okay, so here's another clique. Right, so this clique is also a clique involving those 4 blue nodes, right? So you have the red clique of size 4, you have the blue clique of size 4, and they have a substantial overlap. So the idea, this is the percolation part. So you sort of let sort of the flow of information take place. You say if you see another clique that shares, these vertices, in this case 3 vertices in common, and you can relax that. Okay, so you can make it a little bit more weaker if you want. Then you make that one bigger sort of, cluster or a community. And then keep on doing this. So maybe you find another vertex, right? There might be a third vertex here, and this might share with this, and this, right? So that will also be rolled in. So you basically start from any clique and look at all the neighbors, and if you keep on finding, you keep on growing the cluster, keep on growing the cluster. And you keep on growing this till there is no other thing you can add. Okay, there's no other clique you can add to the thing. So this will then become a dense. So as you can see, because you're doing the percolation, now all the edges do not have to be present. Just that any 2 cliques at least have a few vertices. They have a substantial number of vertices in common. So these are the connected components in this network, and they say these are the clusters. So basically, the idea is first find the clique. Up to size k, and then the second thing is basically do percolation. That is, take a union of all cliques that have at least k minus 1 vertices in common for all cliques. And that basically defines the clusters. This method is also expensive because finding the cliques is an NP-hard problem in the sense that there can be exponentially many cliques in a network. In fact, there is entire just counting triangles, for example, is a hard problem, right? If you look at real-world networks, there are and we're talking about web scale graphs like billions of nodes and edges. So finding the number of triangles, you can actually, many people have come up with actually efficient algorithms just to count the triangles. But now we not only want the triangles, we also want, high order, complete subgraphs. And so that can be pretty large. Okay, so the last thing I want to talk about clustering is, so that's, one other thing. And so basically to wrap up the clustering topic, the only other thing I'll mention is that that one can use other methods, right? So, and we'll see examples of that. So I'm going to be talking about, the classification part. And for the classification, I'm going to be talking about the kernel matrix and, doing some operation on that. So this goes back to the notion of the similarity matrix, right? So once you have the similarity matrix, you can do all the spectral stuff. You can you can do the graph-based stuff. You can also do hierarchical clustering. Right? So you can say that once I have the similarity, it's like a distance matrix, and I can apply hierarchical clustering. So essentially, even though these are graphs, you can actually do many more complex clustering tasks on top of that. So I think that is okay for now because I want to begin the next thing after the break. So we're pretty much done with clustering. Are there any questions on this part of the lecture? So on graph clustering, what we covered yesterday and today, is there anything I can clarify? That's it's a hard question because we did a comparison actually at some point where we looked at different. So one is the evaluation metrics. So modularity is a good metric, but people have proposed some other metrics also. So there is something like cohesiveness, and you can look at the graph structure, and you can say what are the properties of a good cluster, or what are the properties of a good community. And so, in a way, the way you evaluate it, it has to ultimately depend on certain notions you define. You say, obviously, things like it has to have internal edges, minimize the external edges. So there's a lot of variations of those formulas, so to speak. Now, then the question comes, okay, now I have 10 different clustering algorithms I can apply. And what you can do is, you can try to measure what are the properties of the clusters that were found. You can say, if I use modularity, this is the kind of score I get. If I use another, this is the kind of score I get. So now this becomes again sort of a data mining problem, that which of these methods actually performing better, right? Because without any external knowledge, there is no way of knowing. So we can go purely by structural approaches. So the best approach would be if a human or someone else can label some data and say, okay, this actually is a community. So then we can use the external measures that someone has told me what the clusters are, or I knew. So one way to do this would be you generate synthetic data.
So the labels are predefined.
They are predefined, and then you say how well can you predict. But there's obviously a pitfall with that, because then it is synthetic data, it's not real data. So there's always this tension between, So bottom line is, just like in classification there's no free lunch, in clustering there's definitely no free lunch. I mean, sometimes one method may work better, sometimes the other. And essentially, to the extent the results are useful, it's so I mean, I guess you can focus on efficiency. You can say how fast am I, right? So if I'm going to do the Gerber-Newman method, it's going to be too slow. Maybe I do something else and I get equally good results. If I look at the modularity, maybe the Gerber-Newman has a slightly better modularity, but do I really care? Maybe not, right? So I think when you go to large scale, the scale issue, the complexity issue is very dominant, And then you have to say, okay, does it really make if it gives you some insight, then you have to found something interesting. But that validation is always very hard, in clustering especially.
So in ratio cut, we maximize the external rates.
Yes.
And in average cut, we minimize the internal rate.
Yes.
Can we combine these two goals?
Actually, they are, I didn't mention it here, but they are pretty much complementary. It turns out that maximizing the internal is the same as minimizing the external. It's just a different way of looking at the problem. So yeah, it's one and the same thing. But in terms of the mathematics, it's slightly different, but the end goal is pretty much the same.
In MCL, sir, adjacency matrix, we calculate the similarity matrix. It is adjacency matrix, or it is different from adjacency matrix?
So adjacency matrix, normally when you think about it, you think about 0, 1, right? So yes. Something is connected to something else. So when I call it a similarity matrix, it's just a weighted adjacency matrix. Yeah, so it just has to be symmetric and so on. So that's about it.
Both are same?
Yeah, adjacency matrix is, the similarity matrix is basically the weighted adjacency matrix. They're exactly the same thing.
In Markov clustering, how do you calculate the distance between two matrices? Because the step 8 in there is a permitting condition that the distance between two markers.
Oh, that, okay.
Yes, how do you calculate?
That actually is called the Frobenius norm. It's actually very easy to understand. Just take the two matrices and think of them essentially like a vector. Okay, just go row-wise, okay, and the other matrix row-wise, or just like compute element at a time. So basically, if I have two matrices, A, B, C, D, and I have another one, A prime, B prime, C prime, D prime. So this Frobenius norm, right, the difference between the two matrices is pretty much what you would expect. It's the Euclidean distance between these in an element-wise manner. So it's basically the sum, it's basically A minus A prime squared plus B minus B prime squared plus C minus C prime squared plus D minus D prime squared, and the whole thing roots. Just like a Euclidean distance. So basically element-wise, so that's, they have a name for it. It's called the Frobenius norm. It's a very fancy sounding name, but it's essentially a Euclidean distance between the elements of the matrix. And you can use other norms, but this is one of the norms to define the difference. Anything else? Okay, so I guess this is a good time to take a break, right? So we'll take a 5-minute break. And then we'll start classification.